Welcome everybody to section 4.2, dealing with approximating area between a function and the x-axis. So it may look a little surprising that we're actually going to start this lesson with a little review of sigma or summation notation. Okay, that's this sigma guy right here. Okay, so with sigma notation, the variable is this guy down here is called the index variable. That's the letter we're going to be subbing values in for. So we're going to be subbing in numbers for I that go from 1 until we get to the number on top, which is just some arbitrary value n. Okay, so what this would look like if I start subbing in the values for I would be x sub 1, and then we add the terms together. Then I would sub in the next value 2, the next value 3, so on and so forth, until we get up to that nth value, however many there may be. Okay, and so let's go through and just practice some of these, and then we'll tie it all together with this area lesson. Okay, so in this one that's labeled number 1, I have the summation as I goes from 1 to 3 of the constant 2. Now, while it doesn't look like there's really anywhere to sub the letter I in, when you do a summation with a constant, you're basically going to just add this number this many times. So basically this is like the first 2 plus my second 2 plus my third 2, and at the end of the day that is 6. Okay, in the next one we have I going from 1 to 6 of I, so I'm going to sub in 1 for I, then 2, then every number all the way up to 6. Okay, and if we wanted to add that up, we would get 21 at the end of the day. So the summation as I goes from 1 to 6 of I is 21. Now, any letter can typically be used for these index variables. You'll see that in this class, the most common letters are I, J, K, sometimes N, but typically I, J's, and K's. Really, they can be anything, okay? But just pay attention. So here we have the summation as J goes from 1 to 4 of J squared. So I'm going to sub 1 in and square it. Plus 2 squared, 3 squared, finally 4 squared. Okay, and again, we could certainly go ahead and add that all up, and we would get 30 here. And in the fourth example, we have the summation as k goes from 1 to 3 of k cubed. So I'm going to sub 1 in for k, and I'm going to cube it, plus, I'll sub in the next number, plus until we get to that top number. So 1 cubed plus 2 cubed plus 3 cubed, that ends up equaling 36. Okay, 1 plus 8 plus 27 here. The next one up, the summation is I goes from 1 to n. Again, when we go to n, it's just some arbitrary number that n could represent of f of x sub I times delta x. So again, the only thing we're subbing in for is the letter I, which is right there. So I would have f of x1 times delta x plus f of x2 times delta x, plus so on and so forth until we get up to f of x sub n times delta x. And basically we're looking at the y value of a function times some change in x here is what that represents. Okay, and you'll see this again in the lesson. Okay, but there's some basic review of summations. Let's go through a couple of more, and then we'll go through some rules here. Here's the summation of 2i as I goes from 1 to 4. So I'm going to have 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4. And if we add all that up, we are looking at 2 plus 4 plus 6 plus 8 is 20. Okay? Now what I want you to notice about the next one in number 7 is pretty similar to number 6. In fact, the only difference is that instead of having this constant 2 inside of the summation, I've moved the 2 outside of it so we can see what effect that has here. So this is actually twice the summation as I goes from 1 to 4 of I. So this is going to be twice what we get for the summation. Now as I do the summation from 1 to 4 of I, it's just 1 plus 2 plus 3 plus 4. Well, if we add up that inner quantity, we get 10, and 2 times 10 is 20. The point is, notice these two came back exactly the same. It doesn't matter if the constant is within the summation or outside of the summation, it's going to come back the same. Okay? And again, I'm going to formalize these in just a moment for you. And the next two examples kind of go together here as well. The summation as I goes to 1 from 4 of quantity I plus 2. So we would first have 1 plus 2 plus 2 plus 2 plus 3 plus 2, and finally 4 plus 2. And we're looking at 3 plus 4 plus 5 plus 6. And that is going to add up to... I didn't actually add it up. Let's say 3 plus 4 plus 5 plus 6 is 18. Okay? And now look at number 9. I basically have something similar to 8, except instead of having the sum inside of a single summation, I've broken it up into the sum of the individual terms, still both i's going from 1 to 4. So let's see what happens here. Focusing on this first one, that's going to be 1 plus 2 plus 3 plus 4. Plus the second one, the summation of 2 as I goes from 1 to 4. We're going to add the number 2 4 times. 2 plus 2 plus 2 plus 2. Well, if we add all this up here, we've got 10 plus another 8 is again 18. Notice that these two came out the same. Okay? And so that leads us to a couple of rules here. Here's a couple summation rules. Number 1, the summation as I goes from 1 to n of k a sub I, where k is a constant. We can move the constant out in front of the summation and do the summation as I goes from 1 to a of a sub I. Those will be the same, okay? So we can move constants out front. The sum or difference of two summations, as long as these are the same, can be broken up into their own summation. So this can be broken up into the summation as I goes from 1 to n of a sub I, plus or minus the summation as I goes from 1 to n of b sub I. Okay, so basically what that's saying is if you're adding or subtracting terms within a summation, if you needed to, if you wanted to, you can break it up into individual summations. And you'll see how that comes into play a little later, okay? A couple theorems here. Now look, grinding these out really wasn't any big deal because I have small numbers of values, k going from 1 to 3, j going from 1 to 4. But what if I did the summation as k goes not from 1 to 3, but say 1 to 30? We're not going to want to write 1 cubed plus 2 cubed plus 3 cubed all the way up to 30 cubed. That's not even all that tedious, but it would take a lot of time. What if I want to go out to 3,000? Okay? You can see that this could get very time-consuming and tedious, okay? So we have these theorems that I'm going to go over with you, okay? And you're going to want to keep these theorems handy for later on in the lesson. So take good notes here and have this information handy, okay? Here, C is a constant. The summation as I goes from 1 to n of a constant is just that constant times n, okay? If we come back up here, to example 1, we had the summation as I goes from 1 to 3 of the constant 2. Well, the rule says that that's just going to be n times c, which is 3 times 2, which is 6, which clearly matches what we got up above. But now, if I had the summation as I goes from 1 to 3,000 of the number 2, very quickly you can say, oh, it's going to be 2 times 3,000, that's 6,000. Very quickly get that summation, okay? The summation as I goes from 1 to n of just I can be shown to be equal to n times n plus 1 divided by 2, or if you distribute n squared plus n divided by 2. Okay? So that's a shortcut now. So for example, if we go back to number 2, that's the summation as I goes from 1 to 6 of I. Okay? So the summation as I goes from 1 to 6 of I is supposed to be n, which was 6, times n plus 1 divided by 2. That ended up being 6 times 7 over 2. That's 42 over 2. 21 on the nose, same exact thing when we grinded it out. Okay, so just showing you that these formulas work. For the I squared one, the summation as I goes from 1 to n of I squared can be shown to be equal to n times the quantity m plus 1 times the quantity 2n plus 1, all divided by 6. If you wanted to clean the numerator up, 2n cubed plus 3n squared plus n, all divided by 6. Okay, but again, going up to the example here to show you it worked, that would be number 4. Here n is 4, and we have the j squared summation. So the summation is j goes from 1 to 4 of j squared. It should be, what did we say here? I'm going to reference this. N times n plus 1 times 2n plus 1 over 6. N times n plus 1 times 2n plus 1 over 6. So what do we have here? We've got 4 times 5 times 9 is 20 times 9 is 180 divided by 6, which sure enough is the same thing we got, 30. Okay? And one more that we're going to want to know is for the cubed function. And the summation as I goes from 1 to n of I cubed is equal to n squared times n plus 1 quantity squared over 4, or if cleaned up in the numerator, done out, n to the 4th plus 2n cubed plus n squared all over 4. And once again, if I go back to the cubed one, that was number 4 here. Okay, we said it was n squared, so here n is 3. So it's going to be 3 squared, 3 plus 1 squared divided by 4. Let's see. That's 9 times 16, right? 4 squared is 16 over 4. Let's simplify that. 9 times 4, the same 36 we got before. Okay, so look, these are handy. We're going to do stuff with these, so you're going to want to keep these near you, okay? So let me show you an example of how we can use these rules and theorems to do something like the following. Let's evaluate the summation as I goes from 1 to n of I plus 1 over n squared for the following values of n. N equals 10, 100, 1,000, and 10,000. Now keep in mind, like if n equaled 10 and we're actually writing this out, that's what that would look like, and I would have to write out, you know, I'd sub in the 1, plus sub in the 2, plus sub in the 3, all the way up to 10. Imagine going out to 10,000. So we'd have 10,000 squared in our denominator, and then we're going to literally have 10,000 terms to write out. Plug the 1 in. 2 over 10,000 squared. 3 over 10,000 squared, all the way up to 10,001 over 10,000 squared. That would take you a considerable amount of time, okay? And certainly we're not going to do that, and we don't have to because that's what these theorems tell us. They allow us to do this, okay? So now let's see how do we go through this, okay? So basically, I'm not even going to worry about the value of n right now. I'm going to use the theorems to clean this up. Okay, and so here's how it's going to look. Summation as I goes from 1 to n of I plus 1 over n squared. The index variable is I. N is really just some constant. So the first thing I'm going to do is I'm going to factor out the constant, which in this case is actually 1 over n squared. That's not the variable here, I is. So I'm taking out 1 over n squared, and this now becomes summation as I goes from 1 to n of I plus 1. Okay? Now what I'm going to do is I'm going to take this sum that's in a single summation, and I'm going to break it up into the two summations using rule number 2. Okay, so I used rule number 1 to factor out the 1 over n squared. I'm using rule number 2 now to break this one summation into 2. So I'm going to have 1 over n squared out front times the summation as I goes from 1 to n of I plus the summation as I goes from 1 to n of 1. All right. Now what we're going to do is we're going to use the theorems to sub in what these two things equal. So out front I've got 1 over n squared, and now, again, you don't really have to memorize these, but have them handy. The summation as I goes from 1 to n of I. That's n squared plus n over 2. Okay, n squared plus n over 2. The summation now of the constant 1 as I goes from 1 to n. Well, that was the first theorem, a constant times n. That's 1 times n here. What's 1 times n? Just n. And so that's what those summations will end up being based on the value of n. Now what I'm going to do is clean this up a little further. I'm going to distribute through, so we're going to have n squared plus n over 2n squared plus n over n squared. And I'm actually going to get a common denominator just to clean this up a little bit. So I'll multiply this by 2 over 2, okay? So we're going to have n squared plus another 2n all over 2n squared, or in other words, n squared plus 3n over 2n squared. Cleaning up a little further, I can factor an n out of the numerator. which will cancel 1 power in the denominator. And so at the end of the day, what we showed was that the summation as I goes from 1 to n of I plus 1 over n squared can be thought of as n plus 3 over 2n. Now we can go ahead and sub all those various values in for n and see what these summations would equal. And we didn't have to work too hard to get there. So for n equals 10, I would plug 10 in. I get 13 over 20. If I use a calculator, that's 0.65. When I plug 100 in for n, I get 103 over 200. Punching that in, I get 0.515. When n equals 1,000, we get 1,003 over 2,000. That's 0.50150. And when I go all the way out to 10,000 for n, 10,003 over 20,000 is 0.50015. What does this seem to be getting closer and closer to the larger n gets? Looks like as n gets bigger, goes out to infinity, this sum is approaching 0.5 or 1/2. And in fact, if you look at this and you take the limit as n goes to infinity, since the powers of n on top and bottom are the same, you should see that yes, as n goes to infinity, that will approach 1/2. Okay? And so you'll see a problem similar to this in the homework. All right? So take your time going through that using these theorems and these rules, okay? And we're going to apply these even more as we start now talking about area approximation. Okay, so you'll see the tie-in in just a little bit. Okay, area approximation. Let's suppose we have some function f that is continuous on the interval AB. And for now, we're going to deal with functions that are strictly positive, meaning they lie above the x-axis, okay? We want to figure out what is the area underneath the curve and above the x-axis. That's what we're looking for here, okay? And what we do to do that is we do what are called rectangular approximations, okay? And there's all different types of ways we can do this. Today, we're going to look at these things called lower and upper sums, okay? So one way that we can find, or approximate, I should say, the area under a function is to draw rectangles. So what I'm going to do is I'm going to take, this is the entire interval from A to B. I am going to slice it into some number of sub-intervals. So these guys are called the sub-intervals. Okay? And what we can do, let's see, 1, 2, 3, 4, 5, 6, 7, 8. I'm going to do the same thing here. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to show you two different ways to draw in these rectangles. The first of which is going to be called a lower sum, or lower sums. The other I'm going to demonstrate are upper sums. Okay? Lower sums. Basically, each of these subintervals is going to represent the width of a rectangle. Okay? So, and they're going to be equal widths. These are all equally spaced apart. Okay? What I'm going to do do a lower sum is I'm going to ask myself which side of this subinterval, the left side or the right side, which side is lower? Well, it's the left side in the way I've drawn this that's lower. So what I do is I go up to the lower side of the function on the subinterval, and that's going to define the height of that rectangle there. So there's the height of the first rectangle. I used the y value at A. Now on the next subinterval between these 2 points, again, it's the left side that's lower. So I'm going to go up on the left side to the function and put a dot. I'm going to draw a horizontal line, and there's the rectangle there. And I'm going to continue this process. Basically, I'm going to keep going up on the side of the subinterval that's lower. And I am going to get a series of rectangles that are going to approximate the area under the curve. Okay? And so now what we would do is we would find the areas of all these rectangles, add it up, and we would have an approximation to the actual area under the curve. Well, one thing you should notice is what's our approximation compared to the actual area? Well, if you notice, these are inscribed rectangles. They lie inside of the region. And you should notice that we've got a little bit of area under the curve that we never really account for. So These are going to be a slight under approximation to the actual area. Okay? And those are called lower sums when we find the smaller of the two y values to go up to on the function. Okay? All right. The notation for this is lowercase s sub n. That's the notation for lower sums. Upper sums is the opposite. Instead of going up on the lower side to define the height of the rectangle, you go up on whichever side is higher up on the function. So again, side A takes me up to this y value. This takes me up just a little higher. So that's how I'm going to draw the height. On the second subinterval, the right side is taking me a little higher than the left. That would be the height for that rectangle, so on and so forth. So let me draw these in. And they're not perfect, but hopefully you see the gist here. Okay, the difference between upper and lower sums. What we have here now are rectangles that stand taller than the function. So this is going to be an over approximation, and these are called circumscribed rectangles. And this is an over approximation to the actual area. And instead of using lowercase s sub n, we use capital S sub n for the notation for upper sums. Lowercase s for lower sums, capital S for upper sums, okay? Now, in terms of these subintervals, as long as the rectangles are all equal width, okay, what we call the length of the subinterval is delta x. Right, that change in x from left to right. Okay, so delta x is the length of each subinterval. Delta x is just the length of the entire interval, which is b minus a, divided into n number of subintervals. Okay, so there's the formula for the delta x. Okay, and again, what we should notice is that the lower sum area is going to be less than or equal to the actual area, which in turn is going to be less than or equal to the upper sum area. So what we can do to approximate area is get a lower sum, get an upper sum, and then we know that the actual area will lie somewhere in between the two. Okay, so let's see how that works with an example. Find the lower and upper sums for f of x equals x squared on the interval 0, 2 using one rectangle, two rectangles of equal width, and four rectangles of equal width. All right. So just to kind of get a visual here, so here's kind of what x squared is going to look like on the interval 0, 2. Whoops. Got a parabola coming up. Okay. And what's the y value at 2? If f of x is x squared, 2 squared, that would be up at 4, right? So let's do lower and upper sums. So I'm just going to draw it twice. Okay, and in part A, we want to use just one rectangle. So that means that the base of the rectangle goes from 0 to 2. Okay, base of the rectangle goes from 0 to 2. It's just going to be one rectangle. Well, let's look at the lower sum first, and then we'll look at the upper sum. Lower sum on the interval 0, 2. Which y value is higher, the y value at 0 or the y value at 2? Well, the y value at 2 is higher, the y value at 0 is lower. So for lower sums, I would go up at 0, and that would be the height of the rectangle. That's kind of weird. That's a rectangle of height 0 times width 2. That's an area of 0. For the upper sum, on the interval 0, 2, the y value at 2 is higher. So I'm going to draw the height of my rectangle there. And that's a rectangle of area 2 times 4. The height is 4, the width is 2. That's an area of 8. So what did we show? Well, these are both very poor approximations, but what we showed is that the actual area is going to be somewhere between 0 and 8. Well, that's a pretty poor approximation, like I said. So let's see what happens in part B now when we use, instead of one rectangle, we use two rectangles of equal width. So again, I'm just going to kind of set up the visual here. Okay, so delta x, b minus a over n, in this case 2 minus 0 divided by two rectangles is 2 over 2 is 1. So the width of each rectangle is 1. So for the lower sums, on the interval 0, 1, the height is lowest on the left side, so there's the height of the first rectangle. On the interval 1, 2, the height is lower at 1, so I'm going to go up to the function at 1, there's the height. And so basically I'm finding the area of that rectangle plus that, which is 0, to get an approximation. Okay, so let's work this out. Well, look, we need the height of the first rectangle. I'm going to start using function notation for this. I wanted the height at what x value? The height at 0. So I needed f of 0 times my delta x, which was 1. Plus, I need the height of this rectangle. Well, I'm going up to the function at 1. I need the y value at 1. So f of 1 is the height times the width, which is also 1. Keep in mind our function is f of x equals x squared. So now f of 0 is 0 times 1, 0 height, that makes sense there, plus f of 1, 1 squared is 1, times the width. So here we get 0 plus 1, or an under approximation of 1. Using upper sums, again, on the interval 0 to 1, now I'm going to go to the I'm going to draw the rectangle to the higher side of the subinterval. Higher side is at 1. So there's the first rectangle. On 1, 2, the higher side again is at 2. There's, kind of poorly drawn, my second rectangle. And now I'm finding the area of these rectangles to approximate the area under the curve, which clearly, again, is going to be an over approximation. Using function notation, height of the first rectangle, I wanted the height at 1, so f of 1 times a width of 1, plus second rectangle, I went up to the function at 2, so the y value at 2 times our delta x of 1. 1 squared is 1, 2 squared is 4, 1 plus 4 is 5. So now we see that the actual area is somewhere between 1 and 5. So what happened? The interval for the actual area went down, right? We increased the number of rectangles. It looks like we're getting a better approximation. Let's see what happens now if we go all the way out to 4 rectangles. So think about what delta x is going to be with 4 rectangles. 2 minus 0 over 4, 2 over 4, or 1/2 this time. Okay, let's set up for the lower sums here. On the interval 0.5, the lower height is at 0, so there's my first rectangle. On the interval 1/2 to 1, I'm going to go up at 1/2. That'll define the height of that rectangle. On 1, 1.5, it'll look like this. And finally, it'll look like that. Okay? And so our delta x is 1/2 or 0.5, and again we want to do base times height to get the areas of these rectangles. So height of the first rectangle was at 0, f of 0 times our delta x of 0.5 or 1/2, whichever you prefer. Plus, second rectangle has a height at 0.5, so I got to figure out the y value at 0.5 and then multiply that by 1/2. Plus, next one goes up at 1. I need the height at 1. So that's f of 1 times the width of 1/2 for that third rectangle. And for the final rectangle, I need the y value at 1.5 to get that height times 1/2 again. And again, keep in mind for the f values, you're plugging each of those into the x squared function. I will leave it to you to grab a calculator to do so. And when you do, you get either 7 over 4 or 1.75 back for the lower sum. For the upper sums, Now we're drawing the heights on the opposite side of the subinterval. So on 0 to 0.5, I'm going to go up at 0.5 and have a rectangle that's over the region. I'm going to go up at 1. 1.5 for the third rectangle, and 2 for the final. And so again, using the function notation, we're going to have the first height, which was f of 0.5, times a width of a half. That gives me the area of that first guy. Plus f of 1 times a half gives me the area of the second guy. F of 1.5 times a half is the area of the third. F of 2 times a half is the area of the fourth. Again, using a calculator to punch that in, you get 15 over 4, or 3.75. And so now we see that the actual area is going to be between a lower bound of 1.75 and an upper bound of 3.75. So what seems to be happening here as we increase the number of rectangles? Well, you should see that the approximations are getting closer and closer to the true area. Okay? And what's going to give like the best approximation, do you suppose? How many rectangles is enough? You know, if we have this region here and I want to do the best possible approximation, I guess what we're doing is looking at making these things as thin as we possibly can. Okay, I mean, if you think about it, if I get these rectangles super, super thin, I'm more or less going to be filling the region in almost perfectly. So, moral of the story is, to get the best approximation to the area under F, okay, area under F, to get the best approximation to the area under F, we increase the number of rectangles. In other words, let n go off to infinity. Let's have an infinite number of rectangles in here that are infinitesimally thin to fill up this region. Think about like holding a sheet of paper and looking at it from the side. It doesn't seem to have much width, a single sheet of paper, as you look at it from the side. That's very thin. But if you take a whole ream of paper and put it together and look at it from the side, you have quite a bit of thickness. So you think of these as like really, really thin sheets of paper that we're stacking together to fill this region in, okay? And then we're going to get really, really good approximations, okay? And hopefully soon now we'll start seeing the tie-in to our summations here, okay? Because that's what these are. I mean, if you think about it, this is a summation. It's we have the constant 1/2 in each term times the sum of these f of x sub I values, f of 0 plus f of 1/2 plus f of 1 plus f of 1.5, okay? And you'll soon see the tie-in, okay? So hopefully you get the concept, though. To approximate area, we can draw these rectangles either under the region inscribed or over the region circumscribed, lower sums, upper sums. And the more rectangles we squeeze in there and the thinner they are, the better a job they'll do at approximating our area, okay? So that's kind of the gist here. So let's try to tie this to the summations. Okay, so we're going to be talking about these things called left sums and right sums. I was using lower sum and upper sum here. These ended up being left sums over here because I'm getting the height from the left side of each subinterval, right? I got the height at 0 for the first one. For the second subinterval, so this was like my first x value, my second x value, my third x value, my last x value, where I drew the heights. Because they're on the left side of each subinterval, those can also be called left sums. What do you suppose these are going to be called when my first x value came from the right side of the first subinterval? That should be 1, 2, 3, and 4, excuse me, x sub 4. There's my 4x values where I drew the heights from. Okay, these are the right sums because I'm using the right-hand side of each subinterval. Okay? So, in general, okay, for left sums, The ith x value, x sub 1, x sub 2, x sub 3, can be found by doing a plus I minus 1 times delta x. Now, what the heck does that mean? Well, look at what the left sums. For on the interval 0, 2, my first x's value was right at 0. I wanted f of 0. That was my first x value I needed to plug in. That was my x. I should be using 1, 2, 3, and 4 for my subscripts here. Sorry about that, okay? So for my first x value, it was 0. Well, think about that. X sub I equals a plus I minus 1 delta x. So my first x value was a, which was 0, plus plug in 1 for I, and times my delta x. Well, 1 minus 1 is 0 times anything is 0. My first x value was 0. Yes, it was. My second x value was 0.5. So my second x value, a plus I minus 1 delta x, 0 plus, okay, now I is 2. 2 minus 1 times a half. That's 1 times a half is a half. 0 plus a half is a half. My second x value is 1/2. There it is. If I plug 3 in, I'd get 1. If I plug 4 in, I get 1.5, okay? So that formula gives you the x value that you need for left sums. Right sums is a little more convenient. Each x value, x sub I, is a plus I delta x. Coming back here, notice x1 was 0.5. So if I want the first x value, a was 0, I is 1 times a half is a half. That's exactly my first x value was at 0.5. If I plug 2 into that, I get 1. If I plug 3 into it, I get 1.5. I plug 4 in, I get 2. And you can verify that if need be, okay? But this is how we get these x values that we're looking for. If we're going to draw it from x values on the left, a plus 1 minus I minus 1 delta x, where a is the beginning of the interval, and if it's right sums, a plus just I delta x, okay? So what I now want to do is actually, let's do the lower and upper sums for the 4 rectangles here, okay? So check it out. This is from the example, f of x equals x squared, okay? And let's look at the lower sums, okay? So S sub n is going to equal, here's how I'm going to write it. Look, how many rectangles did we have? 4. So it's the summation as I goes from 1 to 4 of f of x sub I, we need the height at the appropriate x value, times delta x. Look, this is height times base. What we're doing is computing the areas of rectangles, and we're adding 4 of those together here, okay? So this is how I could notate this stuff. Well, what we need to do is we need to sub in for x sub I, and we need to sub in for delta x. So delta x here, again, was a half for this example. And x sub I is going to be a plus I minus 1 delta x. So x sub I is going to be 0 plus I minus 1 times 1/2. So x sub I cleaned up is I minus 1 all over 2 if I choose to write it like that, okay? So that's what I'm going to sub in for x sub I, and I'm going to sub a half in for delta x. So let's see where this takes us. So we guess summation I goes from 1 to 4, f of I minus 1 over 2 times delta x, which is a half. All right. Now I need to evaluate the function at I minus 1 over 2. And keep in mind, f of x is x squared still. So if I square that, I minus 1 over 2 squared, if you need to, go off on the side. That's going to be I squared minus 2i plus 1 all over 4. So we have summation. I goes from 1 to 4 of I squared minus 2i plus 1 all over 4 times a half. All right. Yeah, I can clean that up. I can do the 2 times 4 in the denominator. And I get I squared minus 2i plus 1 all over 8. All right? And now look, the index variable is I. 1 over 8 is more or less a coefficient. So what I'm going to do is I'm going to factor the 1/8 out of this thing. And now I've got 1/8 of this summation. Now what I'm going to do is I'm going to break these sum and differences up into their own summations like we saw earlier. So I'm going to keep the 1/8, and now it's going to be summation as I goes from 1 to 4 of I squared minus summation I goes from 1 to 4 of 2I plus summation I goes from 1 to 4 of 1. And then one more thing I'm going to do is I'm just going to move this constant out front here like so, because I like doing that. And now these three summations are in our notes. So going through the notes, let's see, keep the 1/8 out front. The summation of I squared as I goes from 1 to 4. Okay? Well, that was n times n plus 1, 2n plus 1 all over 6. That's the value of that. Minus twice the value of the summation as I goes from 1 to 4. So the summation as I goes from 1 to 4, well, that's going to be n times n plus 1 divided by 2. So there's the value of that summation. And the summation of the constant is a constant times n. That's 1 times 4, which is just 4 here, so plus 4. All right? So we get all this, right? Let's clean it up now a bit. We got 1/8 of what? Let's see. Well, here we've got 4 times 5 is 20 times 9 is 180 over 3. There's 30. Here, I'll cancel these 2's. Oh, that should be 4 plus 1 in there for n. 4 times 5 is 20. And, of course, the plus 4. And what are we looking at here now? We've got 30, 20 is 50, 54 over 8. Which, let's see if I've done this correctly or not. Let me see where I'm at. Oh, nope. One careless little mistake. I see it right away. Little thing here. That should be not a plus, right? That right there is a minus, my bad. So 30 minus 20 is 10, plus 4 is 14 over 8, which lo and behold equals what? 7 over 4, which lo and behold was exactly what we got when we did it out, okay? So this summation notation is working for us, okay? Going from 1 to 4, this didn't save us any work, but if we now broke this into 40 subintervals, this would be much more convenient, okay? And let's see what we get back for the upper sum here. All right, so the upper sum, again, we now want the summation. I goes from 1 to 4, f of x sub I delta x. That's not different. Delta x is still a half for the problem. What is different now is x sub I. For right sums, which is the upper sum in this case, and be careful, right sums are not always upper sums, okay? You have to look at the function you're dealing with. If we had a decreasing function, a right sum would actually be a lower sum here. Notice that the area is underneath that of the triangle, okay? So don't think upper, lower, or always left and right. You really do need to think about it, okay? In this case, left is the lower, right is the upper. But here, for that, it's a plus I delta x, which is 0 plus I times a half, which is just I over 2 here, okay? So there is our delta x sub I, rather, that'll go in there, and we're going to sub in for delta x again. So subbing in, we get the summation as I goes from 1 to 4 of f of I over 2 times a half. Again, we need to evaluate the f function, which is to square I over 2. So we're getting summation I goes from 1 to 4 of I squared over 4 times a half. Summation I goes from 1 to 4 of I squared over 8. So similarly, I've got a 1/8 here, which is just a coefficient. I'm going to bring that out for convenience. And now this is a little nicer than the last one, and that is just the summation of I squared. So again, using our rules from before, summation of I squared from 1 to n is, that was the n times n plus 1 times 2n plus 1 over 6. So here n is 4. 4 plus 1, 4 times 2 plus 1 all over 6. All right. And let's see what we get here. Well, I don't know if you remember, but that's 4 times 5 times 9 is 180 over 6 is 30. So we're looking at 30 over 8, which is the same as 15 over 4, which is the same thing we got back up here when we did it out the longer way. okay, by drawing it and computing those values. Okay, so this stuff all works, okay? Now, what if we want to do this for just an arbitrary number of rectangles? Okay, an arbitrary number n rectangles. N is just some number of rectangles we have, or the number of subintervals, okay? So again, let's look at f of x equals x squared on the interval 0, 2 with n subintervals of equal length, okay? So let's take a look at this. So for lower sums, S sub n, again, summation. Now it's I goes from 1 to n of f of x sub I delta x. So let's get our delta x here. Delta x is b minus a over n, which is 2 minus 0 over n, which in this case is 2 over n. So depending on how many rectangles we have, they will have a width of 2 over n. X sub I is a plus I minus 1 delta x for the lower sums here. 0 plus I minus 1 times 2 over n. So we could write this as 2 times I minus 1 over n, or 2I minus 2 all over n if we choose. Okay? Okay, so we're going to sub in for x sub I and delta x. Let's see where this takes us. So we've got summation I goes from 1 to n. F of 2I minus 2 over n times delta x, 2 over n. Now we need to evaluate the function. Again, we're squaring that out. Take a moment to do that. And when doing that, we get 4i squared minus 8i plus 4 over n squared times 2 over n. Multiplying through the 2 over n, we've got 8i squared minus 16i plus 8 all over n cubed. Okay, so hopefully you're good up to this point. Now I do see a common factor of 8 in the numerator, and believe it or not, the n in the denominator is not the variable. The variable is I. N is just going to be some number. So I'm going to factor the 8 over n cubed out of this thing. And when I do that, we're going to be left with what? 2i squared, I squared. I factored the 8 out. So we're going to have I squared minus 2i plus 1. And now we're making this thing look a little neater, all right? And where do you suppose we're going to go from here? We've got now a sum and difference of pretty nice terms inside of there. We're going to break it up. So I'm going to have 8 over n cubed. First one is going to be summation I goes from 1 to n of I squared. Minus, I'm going to bring the 2 out front, summation I goes from 1 to n of I, plus summation I goes from 1 to n of 1. Again, we are now going to apply our theorems to get these three values. I squared from 1 to n ends up being, I'm going to use the expanded form for this, 2n cubed plus 3n squared plus n. Again, you can find that on the notes, okay? And again, I'm using the expanded form versus the factored form for convenience. You'll see why in a moment. And that was over 6, okay? Minus, I'm going to keep the 2. And then the summation as I goes from 1 to n of I was our n times n plus 1 over 2, or our n squared plus n over 2. And those will drop out. And the summation as I goes from 1 to n of 1 is just a constant 1 times n, and that's plus n. Okay? So let's see what we've got here other than a mess. So I'm going to distribute in here, okay? Let's see what happens when we distribute in here. We're going to get 16n cubed plus 24n squared plus 8n over 6n cubed. Going over here, we're going to have minus 8n squared plus 8n over n cubed. And distributing to the last, we're going to have plus 8n over n cubed. Okay? And now let's go ahead and try to simplify this stuff a little bit. And what's the best way to do that? I don't know, maybe get a common denominator to clean this all up. So it looks like I can simplify the first one a little bit. There's a common factor of 2. So 8n cubed plus 12n squared plus 4n over 3n cubed minus 8n squared plus 8n over n cubed plus 8n over n cubed. So I'm going to multiply by 3 over 3 on these two fractions here. So let's see, we'll have a common denominator of 3n cubed. So we've got 8n cubed plus 12n squared plus 4n, right? Then here we're going to have minus 24n squared minus 24n and plus 24n all over 3n cubed. And now we can clean this up a bit. Look, those 24n's are gone. Okay? And what do we got? We're left with 8n cubed. 12n squared minus 24n squared is minus 12n squared plus the 4n all over 3n cubed. And if we want to rip this apart term by term, we can simplify and we end up with, it looks like 8/3 minus 4 over n plus 4 over 3n squared. There is our lower sum. And now this represents the lower sum for this particular region under x squared from 0 to 2, where we can use any number of rectangles we want. We can use 10, 20, 100, 1,000, and we can get these approximations, okay? So that's what you're to see there. There's the general lower sum now on the interval 0, 2. Let's find the general upper sum. So capital S sub n, again, is going to be the summation as I goes from 1 to n, f of x sub I delta x. Delta x is no different than it just was. That's still a half, right? 2 minus, or not a half, 2 over n. 2 minus 0 over n. X sub I, a plus I, delta x for the upper sum. The right sum here, 0 plus I times 2 over n is just 2i over n. Maybe you're noticing the right sums tend to be a little more convenient. Okay, so I'm going to sub in for these. Let's see what we get here. F of 2i over n times 2 over n. Again, in this example, f of x is x squared, so we're going to apply that to this. If I square 2i over n, we got 4i squared over n squared times the width. And cleaning that up a little further, we get 8i squared over n cubed. Again, the index variable is I. The 8 over n cubed can be factored out front. And now we're going to have 8/3 the value, or excuse me, 8 over n cubed times what we get for that particular summation of n squared, which again you can use n times n plus 1 times 2n plus 1 over 6, or I'm going to use the expanded one again, 2n cubed plus 3n squared plus n over 6. Distributing 16n cubed plus 24 n squared plus 8n over 6n cubed, and then simplifying term by term. 16n cubed over 6n cubed is 8 over 3. 24n squared over 6n cubed is plus 4 over n. And 8n over 6n cubed is again 4 over 3n squared positive. And so there now is the general upper sum just in terms of n. Give me the number of rectangles you want, I'll give you an upper sum approximation. Let's compare the lower and upper sums here. Lower sum was 8/3 minus 4 over n plus 4 over 3n squared, where the upper sum was 8/3 plus 4 over n plus 4 over 3n squared. Notice how close they are. They only differ by a matter of plus or minus 4 over n. It should be obvious that the lower sum here is less than or equal to the upper sum, because here we're subtracting, where here we're adding, okay? What did we say was going to give us the very best approximation, though? The very best approximation is to let the number of rectangles or subintervals go to infinity. Let's take a look at the limit of these upper and lower sums. The limit as n goes to infinity of our lower sum. limit n goes to infinity of 8 over 3 minus 4 over n plus 4 over 3n squared. Well, these are actually pretty nice. Look at where the highest power of n is in the last two terms in the denominator. So limit as n goes to infinity of 8/3 is just 8/3. That's not going to be affected by n. But both of these, the highest power of n is in the denominator, so where do both those fractions approach? 0. And so as n goes to infinity, we have a lower sum that approaches 8/3. Let's look at the limit for the upper sum. That'll be the limit as n approaches infinity of 8/3 plus 4 over n plus 4 over 3n squared. Look at that. 8/3. Again, both of these will approach 0. And what do you notice about the limit for the upper and lower sums as n goes to infinity? They both approach the same value. And what does that tell you? That should tell you that the dead-on actual area under the graph of x squared from 0 to 2 is 8/3. Okay? This gives the actual area. That is it. On the nose. Okay, so let's now put some ideas together with another theorem. Let f be continuous and non-negative. Okay, this is, by the way, the limits of the lower and upper sums. Okay, that's this theorem. Let f be continuous and non-negative above the x-axis on the closed interval a, b. The limits as n approaches infinity of both the lower and upper sums exist and are equal to each other. In other words, the limit as n approaches infinity of little s sub n, which is equal to the limit as n approaches infinity. And watch my notation. I'm going to write summation I goes from 1 to n of f of lowercase m sub I delta x. Well, that limit's going to equal the limit as n approaches infinity of the upper sums, which I'm going to write like this. That should be n. F of capital M sub I to represent the upper sum. Okay, so that's for lower x value, that's the upper, times delta x, which is exactly equal to now the limit as n approaches infinity of our upper sums. Okay, that's the theorem. Where delta x is equal to b minus a over n, and f of lowercase m sub I and f of capital M sub I are the minimum and maximum values of the function, right? They're giving us the lower or higher value on each sub-interval. Okay? And now let's talk about the definition of area of a plane region. A plane region is one that's flat. Definition: area of a region in the plane. Let f be continuous and again non-negative on the closed interval a, b. The area of the region bounded, enclosed, by the graph of f, the x-axis, and the vertical lines x equals a and x equals b. So again, just in general, we have some function f on the closed interval AB. We're drawing vertical lines at A and B, and we're finding this area right here, okay? So we're bound by the graph, the x-axis, and those two lines, okay? And this is given by area equals the limit as n goes to infinity of the summation as I goes from 1 to n of f of c sub I delta x, where, again, delta x equals b minus a over n, and these c sub I values can be any value on the sub-interval, on any given sub-interval. So I'm going to write it like this, okay? I'll write it like this. X sub I less than or equal to c sub I less than or equal to x. I should write x sub I minus 1 on the left side. That's the lower one, x sub I minus 1. Okay, and so this x value, basically what this is saying is c sub I, we can use any x value on each subinterval. Since the lower and upper sums, these limits are going to come back equal, it doesn't matter which we use. So typically, we use right sums because it is more convenient. It is just easier. So we usually let the x value, the x sub I, the c sub I value, whatever you want to call it, be a plus I delta x. And we only do that out of convenience, okay? And so let's go through an example now using the limit definition to find area, okay? So example, find the area under f of x equals x cubed on the interval 0, 1 using the limit definition. Okay? So we need a few things. We're going to need delta x, and we're going to need our x sub I. So again, in general, area is going to be the limit as n goes to infinity of the summation of these infinite number of rectangles, 1 from n, f of x sub I, c sub I, whatever notation you want to use there, just understand what it means, okay, times delta x. So for c sub I, I'm going to do a plus I delta x. Let's get our delta x. That's going to be b minus a over n, 1 minus 0 over n, or 1 over n. So c sub I is going to be 0 for a plus I times 1 over n, which is I over n. Okay? And keep in mind, I haven't said this explicitly until this point. I has nothing to do with imaginary numbers here. Don't get that in your head. This is just the index variable for the summation, okay? So let's go ahead and now sub in for this stuff. So we have limit, n goes to infinity, summation, I goes from 1 to n. Okay, subbing in for c sub I, that was I over n. Subbing in for delta x, 1 over n. Now I'm going to evaluate, so first thing we did was sub that in. Now I'm going to evaluate the function. And I'm cubing here. It's the cube function. So I got a cube I over n. That's not too bad. That's I cubed over n cubed times the 1 over n. Okay? And so we should see we've got 1 over n to the 4th here, and that's what I'm going to factor out front. So watch. Let me write it like this. We've got I cubed over n to the 4th, and I'm going to bring that 1 over n to the 4th out in front of the summation. Okay? And we're taking the limit as n goes to infinity of this thing. Okay? Well, now I'm going to apply my summation theorems for I cubed. So again, you're going to go and you're going to look that up. So we got limit n goes to infinity of 1 over n to the 4th times what we get for the summation of I cubed. And I'm going to use the expanded form of that, which was n to the 4th plus 2n cubed plus n squared all over 4. Let's clean this up. We got the limit as n goes to infinity now of basically n to the 4th plus 2n cubed plus n squared all over 4n to the 4th when I multiply the denominators together. And now we've got a limit. N goes to infinity, and we've got the same highest power on top and bottom. So what is this limit going to approach, folks? It looks like 1 over 4. And that is the exact area under under the graph of y equals x cubed on the interval 0, 1. Let's do one more example using this limit definition. And then in the homework, you're going to have 2 for x and you're going to have 1 for y. I'm not going to do an example of a y one with you. I'm going to see if you can do it, based on what we did in terms of x. So give it a try, and of course, reach out if you need help. But it's basically all the same idea here. Okay, it's all going to work out the same. All right, you're going to be looking for a delta y instead of a delta x. That's really the only difference. Okay, but let's take a look at another example with x. Use the limit definition to find area under f of x equals 4 minus x squared on the interval 1, 2. Okay, so if we think about that, we've got this upside down parabola. The intercepts are at plus or minus 2. And I want the area from 1 to 2. So I'm basically looking at this chunk of area. Okay, we're going to find that area. Okay, so again, area A equals the limit as n approaches infinity, summation as I goes from 1 to n, f of x sub I, c sub I, delta x. Again, c sub I, x sub I, you can, whichever way you want to notate it, that's up to you. Delta x, b minus a over n, ends up being 2 minus 1 over n or 1 over n again. X sub I, I'm going to go with the right side, a plus I delta x, which in this case, a is 1 this time, so be careful, plus I times 1 over n, 1 plus I over n it is. Okay, so there we have our x sub I, our c sub I. Okay, so I'm going to sub this in here, and I'll sub this in there. So we're going to have limit n goes to infinity, summation I goes from 1 to n, f of I, 1 plus I over n, times delta x, 1 over n. Now I'm going to evaluate the function, which again is 4 minus x squared. So I'm going to go off on the side and do that. 4 minus this thing squared. So 4 minus, well, if I square that out, I'm going to get 1, I'm going to get plus 2i over n, plus I squared over n squared. Okay? And if I do 4 minus, I'm going to see 4 minus 1 is 3. I'm going to get a minus 2i over n and a minus I squared over n squared there. So that looks like what I get when I evaluate f of this thing. So here we go. Limit n goes to infinity. Summation I goes from 1 to n. The function became 3 minus 2i over n minus I squared over n squared times our 1 over I. Let's go ahead and distribute this through here, maybe. Let's see, yes or no? No, in fact, you know what I'm going to do? I'm going to move this guy out front. So here we go. Limit n goes to infinity, 1 over n. Summation I goes from 1 to n, 3 minus 2i over n minus I squared over n squared. Okay? And now I think what I'll do is I will rip this one summation into 3 summations. So limit. And again, the reason we do that is so we can apply those theorems that we discussed much earlier. So first summation is that minus. Okay, second summation. Oh, and I need another parenthesis around this for all that 1 over n stuff. Okay, and now I'm going to clean these up a little bit. Like I can bring the 2 over n out front, I can bring the n squared out in front of that summation. So bear with me, here we go. Limit, told you this was very technical, detailed stuff here today. Okay, first summation looks good. It's just 3. Second summation, I'm bringing the 2 over n out front, so all I have in there is the I. And I'm bringing the 1 over n squared out in front of this last one, so I just have the I squared in there. Now I can apply my rules on these things. Okay, so for the first one, constant times n is 3n here. This one was n squared plus n over 2. And for the I squared one, I'm using the expanded form of let's see, 2n cubed plus 3n squared plus n over 6. All right. Okay. And now we've got ourselves a big old mess. So what should we do? Well, I guess we should work on cleaning it up a little bit. And so that's what I'm going to do here. So I guess I'll leave that. And now I'm just going to kind of clean each of these things up real quick. So we got 3n minus 2n squared plus 2n over 2n minus 2n cubed plus 3n squared plus n over 6n squared. And I'm going to go ahead and redistribute the 1 over n back into everything. So let's see, we get limit n going to infinity of, okay, 3n over n for the first term, minus 2n squared plus 2n over 2n squared when I distribute to that. And when I distribute to this, 6n squared times n is 6n cubed in the denominator. And again, very nice thing now, as n goes to infinity, notice all of these have the same highest power in top and bottom. So this is going to work out nice. The limit as n goes to infinity of 3n over n is 3. The next one's going to be minus 1. Watch that sign. And the last one's going to be minus a third. 1 minus 3 is 2. 2 minus a third, 5 thirds, which is the dead-on exact area. So good for you if you made it through this whole lesson. If you had to take breaks, completely understandable, but really technical, gritty stuff. You don't need to memorize the summation formulas, those summation theorems. You just need to know how to use them to get these values. And today, a very technical day, and then once we start doing bounded integrals using the power rule, it will become easier again. So this is kind of like when we did definition of derivative using limits, technical, difficult kind of stuff to take derivatives, but then we found the rules for taking derivatives, and they were easy, kind of the same idea, okay? And this is going to lead into bounded